So welcome, this is electromagnetic waves, and this is, basically going to talk about the fact that I can induce an electric field by having a changing magnetic field, and I can induce a magnetic field by having a changing electric field. And basically back in the day, I'm going to ignore that thing. So back in the day, people played with it, and there were people like Hertz, not the rental car person, but the famous scientist who was basically playing with induction coils, basically. And he found this weird thing. He found that he could cause a spark between two terminals. He could cause a spark here between two terminals. And that would induce a spark in another coil, because they were talking to each other. And he found that actually the induction could be over quite a large area. Now we look back and say, oh, it's like magnetic field, all everything. But for them it was quite amazing. And he immediately thought about, this could be useful. I can send signals. Just the fact that I'm sparking, hey, I'm here. And somebody in another room will know, oh, he's here because he's causing a spark. Communication of some kind or other. But it just goes on way from there. It becomes radio rather than telegraph. And there was a tremendous need for that. So Hertz used an LC circuit as a transmitter and another LC circuit as a receiver. He was able to show that energy moved from the transmitter to the receiver via electromagnetic waves. And the idea is that an alternating electrical field induces an alternating magnetic field, and an alternating magnetic field induces an alternating electrical field. And so it's kind of like one causes the other and one feeds the other. So which comes first? And it doesn't matter. They're ripples, if you like. And this gets really, in a way, kind of confounding. So you have light. And you can do experiments that show that light is a wave. We'll do those next quarter. We can show that light is a wave. Basically, we just use double slits or single slits, and we see the wave nature of light. And it's quite obvious. And you can do other experiments, and you can show that light is a particle. And so you but back in Newton's day, there was huge descent. There were the corpuscular theory people like Newton who said it was a particle, and there was the wave theory people who said that light was a wave, and they were at each other's throats. Because it was so obvious to the wave people that it was a wave, and it was so obvious to the particle people it was a particle, that, how can you see that? Why can you say it's a wave when it's obviously it's a particle? Well, look, how can you see it's a particle when it's a wave? You must be interpreting your bit wrong because I'm right. You must be interpreting your bit wrong because I'm right. Never dawned on them that it could be a bit of both. And it seems like, to my mind, it seems like a silly argument now, although I'm sure it wasn't at the time. It's like, you don't find anybody at Publix with ravioli, kind of really confused, and saying, well, is this dairy because it contains cheese? Or is this ethnic because it's pasta? It's like, which aisle do I put this on? Where do I file this? It's ravioli. It's like, it's a mixture of, it's got some cheese in it, but it's not cheese completely. It's got some pasta in it, but it's not pasta completely. It's a bit of both. It's like, but they couldn't see that. It had to be one or the other, and so there was this huge fight about it. And so what they knew about waves was that waves require a medium. You can't have water ripples without the surface of water. You can't have sound without speech anyway without air. You can have sound going through solid objects, but you need the solid object. They couldn't think of a wave that didn't have a medium. And so the obvious thing was, well, there must be a medium for electromagnetic waves. And so they said, oh, this is the ether. Ether. Not the chemical, but a name. Ether. And the interesting thing is, if you do have a medium, then what that means is that imagine you're on a boat and you are moving across a lake and you drop a pebble in, you see the pebble cause a ripple, but the ripple, as it gets bigger, seems to move behind you. Well, you're moving forwards, but you can't tell by just looking at the ripple. The ripple could be moving away from you. So the idea is, oh my word, if we send light one way versus sending light the other way, and we're going in a circle around the sun, one time this will be going against the ether, and the other time this will be going with the ether. So I should get different measurements for the speed of light depending upon how I'm moving relative to the ether. Just like here, if I'm got my boat going in that direction and I drop the pebble in, then what happens is, because but I should be able to measure the speed of light relative to the ether. And then the next thing is, supposing that there's a flow to the ether, supposing that the Earth, the solar system, everything is flowing through the ether, then it's like I'm flowing against the ether with one experiment. With the next experiment, I'm flowing with the ether. So this would go like that, and then that would be like that, and then that would be like that, and then that would be like that. I would get different results depending upon when I did the experiment, because at this time I'm going against the ether, and this time I'm going with the ether. So then if I can look at that, I can interpret how the Earth moves through the ether, and I can find out, is the solar system stationary in the ether or moving in the ether, and how are we doing? You know, what's going on? I can get directionality. Directionality is in that direction, and now I'm going in that direction. So they tried it, and they never found a difference in the speed of light. There should have been. And they said, well, the Earth drags the ether with it. So they put these very delicate instruments in balloons and sent them up into the upper atmosphere and did the experiment. And they never found a difference in the speed of light. And they just flummoxed them. They couldn't find this medium. And then just to I'm going off topic here, but then it was actually the most famous name for it was people like Albert Einstein, who basically said, there's no ether. You know, just accept it. We didn't find it. There's no ether. Now, what else has to change to make the physics work?
The nature of light.
And so he changed the nature of space-time. And he was like, all that crazy math, all that crazy ideas, length contraction, and the like, all of that came out of that acceptance of the fact there's no ether. So sometimes, you know, I mean, I guess the thing I learned over my career is you're not going to get a PhD for being really good. You're not going to get a Nobel Prize for being really good at physics. There's a ton of people who are really good at physics. It's a requirement, but it's not the next thing. You've got to be really good at physics, and on some level you've got to say something which is just amazing. or maybe famous.
You mean crazy?
You're not going to get famous by saying me too. You're going to be famous by saying, you know, this is that, and everybody goes, you're crazy. And then you find, yeah, this is that, I'm right. That's where you get famous. We like Newton, we know Newton 400 years because he said stuff that was just amazing. No one believed, and it was true. And same for Einstein. No one believed it, and it was true. It captured the people's imagination because what he said was, on the face of it, ridiculous.
We didn't see anyone disbelieve them. I mean, they proved them wrong.
That's been tested so much, and no one's proved it. It's like,
It's not come up.
so,
It's complete.
let's have a look at this. So basically what we say is, so let's go back, I've missed a slide, so let's go back and say, okay, so let's recall Maxwell's equations, and we did the first one, that was good old Gauss's law, and the second one we touched on, that was magnetic Gauss's law, and then we did the third one, and what was this one? Integral of EDS, it's good old, whose law is this? Was it Faraday, or was it Ampere? Ampere's law, and then we did this basic bit, which was, am I right on that? That's Ampere's law. So this guy's, you know, my law. This is Bonaquisti's law here. So, E dot ds equals d phi by dt. Anyway, 4 laws. Let's take the last two, which we kind of flew over, and we'll kind of fly over them again. So E dot ds is equal to minus d phi b by dt, and the integral of b dot ds is equal to mu naught I. And then we had this, basically, this little fudge term at the end. If we look at that one in particular, well, solving gives d2e by dx squared equals mu naught e epsilon naught d2e by dt squared, and d2b by dx squared equals mu naught epsilon naught d2b by dt squared. So we have two wave equations. Both equations have the form of the general wave equation. The general wave equation was d2y by dx squared is equal to 1 over v squared d2x by dt squared. And we kind of touched on that for mechanics, oscillations and waves. And then we said, oh, by analogy, if that is 1 over v squared, then that is 1 over v squared. So that must mean that the speed of light is equal to 1 over the square root of mu naught epsilon naught. And when they worked it out, that turns out to be, what was it? 3 times 10 to the 8 meters per second. So it was right. They experimentally measured the speed of light, and sure enough, it worked out to be the same as this. So it's kind of pulled out of a hat.
Just the speed of light?
C is the speed of light. So what we can say from this, there's 3 bits I need you to know. First bit, speed of light equals E over B, which equals E max over B max. Okay, there's the first equation. E over B. Okay, so they sound similar. You got to know them because it's not symmetrical. So you could do it this way. This is the way I remember it. B max times C is equal to E max. It goes in the order of the alphabet. Okay, it's not perfect, but it kind of helps you. Consider an electromagnetic wave. If the maximum component of magnetic field, so E max, equals 2 millitesla, what is the maximum component of B max, electric? I did the same thing last year, it's interesting. E max. So we said B max times C is equal to E max. So B max is equal to E max over C. So B max is equal to 2 times, oh, sorry, no. Where am I going? E max. So B max is 2 times 10 to the minus 3 times 3 times 10 to the 8 is equal to E max. So E max is equal to 6 times 10 to the 5. What are the units going to be? What are the units going to be? Newtons per coulomb. Alternative units? Volts per meter. We can define, if you look back at this thing, these guys are always at 90 degrees to each other. So, E and B are always at 90 degrees to each other. And they affect each other, and we can define this thing called a pointing vectors. We made up area vectors, we can make up a pointing vector. P-O-Y N-T-I-N-G, not pointing, but pointing. It kind of points as well, but it tells you the direction at which the light goes. And basically, we can say that S is defined as being 1 over mu naught E cross B. The magnitude of the pointing vector represents the power per unit area along the direction of propagation. So it's the intensity. Power per unit area is intensity. So this is the intensity of the light. The intensity of the light is equal to the average pointing vector, which equals E max, B max, over 2 mu naught. So, okay, I can substitute in for this, can't I, if I want. So my advice is you say I is equal to E max, B max, over 2 mu naught. And you also remember what you just learned, which was B max times C is equal to E max. So if you need to combine these, you can develop a third equation, which would be our third and fourth equation. It would be, let's have a look, it would be C times B max squared over 2 mu naught. Or you could have substituting the other way, where you say that would be E max squared over 2 mu naught C. But either way, I would only learn that bit because I already know that bit. So what's going to happen here? I could tell you an intensity of light and ask you for a B max, or I could ask you for an E max, or I could give you a B max or an E max and ask for an intensity of light. The radiant energy of the sun comes as a plane wave of intensity 600 watts per square meter. So I is equal to 600 watts per square meter. What is the peak value of the magnetic field? B max. So what does this, what did that expression just say? What was that first big equation? I equals C. Oh, give me it in the original. What was the?
Oh, the original?
Yeah.
E max, B max over 2 mu naught.
E max, B max over 2 mu naught. And then we know that B max times C is equal to E max. And I want things in terms of B max, so I want to get rid of that E max. So I is equal to B max C times B max over 2 mu naught. So now I get B max squared is equal to 2 mu naught I over C,
True.
which equals 2 mu naught. My intensity is 600 over 3 times 10 to the 8. So that equals 1200 over 3 times 10 to the 8 times mu naught. So B max squared is equal to 400 times 10 to the minus 8 mu naught Tesla squared. So B max is equal to the square root of 400 times 10 to the minus 8 mu naught Tesla. And you can leave it like that. That's the second skill. There's a. You ever been to Mosey and seen those little light bulbs that have the little black and white squares in them? They spin in sunlight.
No.
So they are often called radiometers, and there's a Crux radiometer, and I think it's a Landau radiometer. And it turns out that the one we want is the one you don't get at Mosey. The one you get at Mosey is the Crux radiometer. And what happens is that I'm going to just show one set of vanes. So one surface is dark and one surface is light. So, and they're hinged together and they spin around that point. What happens is what happens is that the white surface reflects the sunlight and so stays cool, whereas the dark surface absorbs the sunlight and gets warm. And in getting warm, it heats up the air on the dark face, and that expands and pushes the thing. So this spins that way with the white surface at the front. Agreed? Everybody follow that? Yeah. Heat up the black surface heats up the air expands, because there's a little partial pressure of air inside there. It's not maybe atmospheric pressure, but it's, there's some air in there. We get a spinning, and if you look at it, it's the white face that's coming towards you and the black face that's been pushed away from you. Yeah. That's a Crux radiometer. I think it's the Landau radiometer. The Landau radiometer has the same design. What happens here is a photon of light comes in and bounces off. And here a photon of light comes in and is absorbed. And we know that my force is equal to my change in momentum, which equals P final minus P initial, which equals mv final minus mv initial. So let's just make up numbers for this. So that would be 1 times minus 1, because it's going in a negative direction, minus 1 times plus 1, because it was coming in a positive direction, which equals minus 2 MVs, kilogram meters per second. Whereas on the dark face, we have F is equal to delta P, which equals P final minus P initial, which equals 0 minus mv, which is 0 minus 1 times 1, which equals minus 1 kilograms meters squared. So there's twice as much force on the white face as there is on the dark face. And so it rotates in the opposite direction. But it does rotate because of the photon bouncing off versus the photon not bouncing off. And this is a true effect. Photons have, any mass. Don't think so, but they have momentum. I cannot explain that to you at all. But you can measure this effect, and you can make a Landau radiometer. Difficult, they're expensive. You've got to maintain no atmosphere, what to speak of. Perfect axes. But you can do it. In fact, they used this when they were on one of the early space shots. The Mariner or something was not on the right trajectory. They need to turn it slightly. And so they had the two solar cells, and they turned one solar cell out of the sun. So made one solar cell's plane parallel to the rays of the sun, and they turned the other solar cells into the plane of the sun, and they got a turning effect. It took a while, but they got a turning effect. So you can use it. They talk about solar sails. They talk about, free engine. You just put a big sail up and it catches sunlight and just continues. So this is where this is coming from. And basically what it says is we have a dark side and a light side. And basically what we say is that the momentum is equal to the energy over the velocity for the absorbed light. If it's reflected, it's 2 times that. We have twice the amount of momentum. Momentum transfer creates a pressure. It's the force per unit area. And this is going to be 1 over the area times dP by dt, good old Newton again. So the pressure is equal to the force per unit area, which is 1 over the A dP by dt. So that's 1 over A du over C by dt, which equals 1 over C du by dt over A. And recognizing that this is the Poynting vector S, we get that the pressure is equal to the Poynting vector over C. And we can work out the pressure. This should be in Newton meters. And frankly, when I used to give you the equation sheets, this was fair game, but nowadays, just know it can be done. Okay, so don't worry about this in terms of the equations. Just know it can be done. Okay. So, we've been talking about radio communication, and then we're talking about light, and it's like, hold on, isn't that different sections? And it turns out it's not different sections. It turns out that what they realized is that electromagnetic radiation is basically the same as light. It's got the same speed, has the same properties, got different frequencies. I'm sorry?
It's still measured with the sinusoidal waves?
Oh, electromagnetic waves are sinusoidal, yeah. Yeah. So, and so bit by bit they piece together the fact that there's a whole range of electromagnetic radiation, and we see it in different bits of science, and we tend to think of it as being different bits, but in fact it's all linked. So if we go from, and so what causes EM radiation? Basically the acceleration of charged particles. That's pretty much what does it. So a big radio tower, when you think about it, a big radio tower is a big piece of wire. And it's got a big generator at the bottom of it, and it is basically effectively sending current up and down that big piece of wire at a certain frequency. And that's the frequency of the EM radiation. If you like, if you want to be a bit loose on language, it's the frequency of light that that radio tower is sending out. It's glowing just like a light bulb. It's just glowing with light we cannot see. The sun creates light by accelerating charged particles. It accelerates them in the photosphere. Actually accelerates them in different places, but the ones that we can see that have the right frequency, because they have the right vibrational mode, because they have the right temperature, are the ones in the photosphere. It turns out the temperature of the sun's atmosphere is much higher than the surface of the sun. If you said, I want to send a spaceship to the surface of the sun, it would melt before it got there, because it's going through much higher temperatures. But we can't see that because the temperatures are too high for us to see. You go to the doctor's office, you get an x-ray, they fire electrons into a copper target, cause deceleration, you get light given off. You can't see that. You put your meal into the microwave, you press that button, ignoring the light that comes on, which is a light bulb saying I'm on. There's coils inside which glow with a colour that we cannot see, caused by changing charged particles at frequency that is just right, and that causes the food to oscillate, the electrons and the food to oscillate, which warms them up. Just a little interesting by-story. Back in the day in Gainesville, they had, I think it was GE, had a factory which worked on microwaves. And they were interested in it for military applications. And they decided microwave weapons and stuff like that. And they gave up on it. And about 10 years later, somebody was like, oh, every time I put my lunch on top of the apparatus, it gets warm. Oh, maybe I can make a microwave oven out of it. And the first microwave ovens were lousy because they would leak radiation quite badly. Oh yeah, they were bad. And that gave them a really bad name, and then they cleaned up their act, and so now you don't think about it. But, you know, there's a reason why, on that glass plate, there's a reason why it looks like a wire mesh in the glass. It's because it's a wire mesh in the glass. They are using a Faraday cage to make sure that it stays in there and doesn't leak out. And I worked with people, because they use microwaves as heating sources all the time in scientific equipment. And I work with people where, I mean, imagine you're working on a Van de Graaff generator or something, and you've got this microwave heating source up in the top, and you've got to try and fix it, but you've got to kind of climb up to do something, and climb down to turn on the switch, and climb to do something. You've got to be really careful around those, because you might get somebody working on it who's not that familiar with the system, might know his little bit. It's tempting to say to somebody, just turn it on and see if I connected it right. Right next to a microwave source, which is really bad. So all of these things are the same. They are the same. They are the same. They're just different colours. Biologically, we decided to make eyes that are sensitive to the colours of the sun. So we biologically chose to see reflected sunlight. So we see during the day. And we sleep at night. We made a choice. We said, rather than having eyes that can see the tiger in the distance, I'm going to hide at night. So basically, we sleep when it's dark, and we are awake when it's light. But we can make cameras now. We can make cameras where I can track you. I don't have to. I just need to. If you're, especially on a cold night, if you're walking and there's not many people around, I can track you just by looking at the way your foot heats up the pavement as you walk. I can track your tracks using infrared. I was at a trade show in Japan, and the company opposite made an infrared camera, and people want people to come to their exhibits, so they do stuff. I went to one place and they had they were selling some technical gizmo, and they hired a magician. And the magician would come and do card tricks, and people would gather round. And then at the end of his thing, all the sales guys would come in and try and get sales leads for it. And it's like, do you really think that's going to make a difference? But they did. So there's always these kind of gizmos. And this one guy, he had this thing where he'd hold up his hand and it'd be red. Oh, false colour. It's not red. It's infrared, but it's showing it on a computer monitor as red. And he'd light a cigarette and it would turn blue. And that's because the cigarette constructs his blood vessels, his hand cools. You could show it, showing the sensitivity of these things. So we see this little bit here. If we go from temperature point of views, if we go hotter, we go towards X-rays and gamma rays. If we go colder, we go towards radio waves. Not all of these radio different colours make it through the atmosphere. The atmosphere lets through visible light, blue better than red, is not so good for X-rays and gamma rays, thank heavens, or else we'd be X-rayed all the time and gamma rayed all the time. So it protects us from those. It lets through a lot of the radio, but not all of the radio. And so the revolution in astronomy that's taking place now is the fact that for the first time we have eyes, detectors, that are able to see all these wavelengths. We have radio systems that can see very long wavelength radios. We have gamma rays. In fact, China just launched a gamma ray telescope. America had one before, Europe had one before. So for the first time we can look at things in all the colours, which means all the temperatures. So good question or comment?
Yeah, so we're unable to see the light wave with the naked eye, correct?
No. What do you mean by that?
Like seeing actual the wave from the produced by light.
Yeah, the electric field. But remember, the electric field is an abstraction. You could never see the wiggly thing, because there is nothing going wiggly apart from an electric field, and that's an abstraction. So this whole thing, this is where it gets mysterious. What is a photon? It's energy. That's the best you can say. It's energy. So, can you see it?
No.
But you do see it, because it hits your eye. So, it's like you do see light when it hits your eye. You don't see it when it's passing, because it's nothing to be seen. It's the weirdest thing. And you either love that, or you hate it. So, it's there. Let's call it a day. Yay.